So, yes, well, this is intended to be a very gentle, non-mathematical introduction to machine learning. And hopefully I'll convey a flavor of what it is that machine learning can bring to visual analytics. I appreciate that many of you will already be familiar with machine learning or use machine learning techniques. But I hope to convey a sense of the scope and get on some of the state-of-the-art stuff. So hopefully there'll be something for everyone. So if you were going to look at the main machine learning capabilities, you could probably divide them up into three different areas. Prediction, recognition, and pattern mining. So all the sorts of machine learning applications you've come across: biometric, identification, stock market prediction, recommender systems, sentiment analysis, fall somewhere within the Venn diagram that connects those. And I guess visual analytics can potentially draw from all of those capabilities, so it would be located somewhere at the center of the Venn diagram. And it's not just a case that you can have data as a given, you can also have humans in the loop, or use machine learning for human-computer interfacing. So this is one example that I'm involved in, looking at recognition of cancerous material in mammograms, but instead of treating this as a computer vision problem where you try and find features in the mammograms and classify those, here you have a human, an expert that can recognize.
We want to do the lecture capture, so we need to go through the VJ.
There's a problem. It didn't seem to work.
Okay. Sorry about it. We'll carry on this.
Okay. So normally you would have a straightforward computer vision problem, and you would turn the mammograms into features and try and classify them. Here we've got a human in the loop. So we're actually presenting these mammographic images very rapidly to a human, taking advantage of the fact that human recognition is actually pretty fast, a lot faster than verbalization. So rather than have the computer do the whole image processing pipeline, here we're having the EEG signals from the human brain, and we're trying to classify the recognition signal to see if there's tumorous material. So it illustrates the very standard sort of pipeline for machine learning. You have some sort of data acquisition, you have various bits of signal pre-processing, then you have feature extraction, typically have some training data, and you then classify that and apply it to the problem, which may have specific issues, as you very often find in medicine, in terms of how you balance the particular classifications. I'll come on to that later. But it's not just single modalities that you typically work with. Very often you can have complex multiple modalities, and I guess this is typically the case in visual analytics. You have data from a lot of different sources. So one exemplar might be biometrics. Here you've got extremely heterogeneous data. You might have fingerprint topology, you might have facial images, iris scans. Hand measurements turn out to be a very effective biometric. Retinal scans. These days, increasingly, you might have DNA, which is a complete different data format. That's sequential data of arbitrary length. You might have voice, again, that's time series data. You might have video sequencing. Gait recognition is a very strong biometric. So the idea is you combine all these together and get a stronger biometric recognition than you would from any individual modality. So these hopefully collectively give you an idea of the sort of range of data that you can apply machine learning to. But to go back to the basics and just see how this is done from the bottom up, typically in machine learning, and this isn't always the case, and I'll come on to some very interesting exceptions to this, but typically you start with a feature space. So you have some object or some individual, say, that has a set of measurements associated with them. These can be very simple measurements, age, weight, and so on. Or it could be much, much more complex measurements. I mean, imagine the sort of complexity you've got in a video sequence of, say, a ballerina, if you're using computer vision. So you have millions of features. But as long as you've got some way of representing a set of measurements as either real, numbered, integer, or binary data, basically you can embed every single object or every single individual into a feature space. So each individual becomes a vector in a feature space. This simple example, you've got 3 people, various ages and weights, so you get a cloud of vectors in a feature space. And in the commonest form of machine learning, supervised classification, you also have labels attached to these individuals. So this is typically something that is hand annotated or expert annotated. So in this case, this might be a problem to distinguish people at risk from diabetes from those that aren't. So you may have a doctor or a team of doctors annotating this data on the basis of their experience, saying, well, I think this person is at risk, I think this person isn't at risk. So you've got a set of binary labels, in this case, as binary problems, and all you can have multiple classes, but they're always reducible to binary problems. So for simplicity, we'll look at binary problems. So you've got 2 classes, non-diabetic, diabetic. So effectively, we've got labeled vectors. Labeling is in color. And the goal of supervised classification is to find the best discriminator. And now this is something that if you've got an n-dimensional feature space, you're looking for an n-1 dimensional manifold that will bisect this feature space into 2, so that you're saying essentially everything on one side of this manifold is going to be of one class, everything on the other side is going to be of another. It doesn't have to be a linear manifold necessarily. So you're trying to find the best. The goal of supervised classification is to find the best manifold, the best discriminator. And the problem is typically only as good as the features you put in. And just as an illustration of that, we've got a non-linearly separable problem in this, if you see the upper diagram there. This is where you've got some single measurement feature, it might be age, might be weight, and basically all your data is not linearly separable. So you can't find an n-1 dimensional manifold, or in this case a single point, that will separate that into 2 classes. However, if you add another feature, and we're not actually adding any new information, and ideally this would be new measurements of each individual, but in this case we're just adding extra data in the form of an age squared feature, or an x squared feature, and lo and behold, the problem becomes linearly separable. So basically the problem of classification is as difficult as the features you put in. So it might sound like features are always a good thing. There is an issue when you get too many features, which I'll come on to in due course. And of course, if you've got an arbitrary manifold, you can imagine that it starts to get parametrically complex if it's non-linear. So here you've got a non-linear manifold, one-dimensional manifold that's trying to separate, trying to build a classifier on the basis of your input data, your labeled training data. And you can see here, it's almost certainly overfitting in the sense that it's trying to capture this little outlying point. So if this were something like a polynomial surface, the degree is basically too high. It's overfitting, and almost certainly this wouldn't generalize. If you presented it with new data, new labeled data, you would actually find that that wasn't a particularly good discriminator. So the complexity of the problem, the classification problem, is crucial. So more parameters, not always a good thing. They capture more morphology potentially, but can easily overfit. And it's even possible if you've got too many parameters and too few training data that the problem is actually, the classification problem is actually ill-posed. So just to give you an illustration of how complex this should be, I mean, the question, how complex is a decision boundary? Well, one way of looking at this is to characterize your cluster distributions in terms of their covariances. So you've got 2 different classes. You've got scatter matrix with a covariance. So effectively, you can model it with a Gaussian distribution. And if you're asking what the best decision boundary would be in this case, the phase optimal decision boundary, if your covariance matrices are the same, and you're drawing from a Gaussian distribution, then you have a nice linear decision boundary. That's the optimal boundary. So you'd hope your classifier would, so a linear classifier could potentially find the best decision boundary in this case. But as soon as the covariance matrices of your classes differ, which is going to be true for just about all data you're ever going to come across, then the optimal decision boundary, even if it's just a Gaussian distribution, which is also never the case, is going to be nonlinear. You see that in the top left-hand corner. So there's no way to say a priori, well, this or that classifier, this or that decision boundary is going to be best. It's entirely data dependent. So something I really want to bring out in this talk is the relationship between regression and classification. So regression, I guess, is more typical in visual analytics. And the typical assumption in regression is that you've got some sort of multivariate trend with noise, and you fit to that. It might be a linear relationship, it might be a nonlinear relationship. And what you're trying to do, in this case being a linear fit, you're trying to fit a model that predicts that the values of a set of dependent variables given a vector of independent variables. One particular way of looking at regression, obviously that can be potentially much more complex relationship, polynomial or whatever. So lots of different types of regressor. And regression, like classification, they share the issue that they're only as good as the assumptions you put in. So this particular set of data, known as Anscombe's quartet, I think are a really good illustration of this. So basically what we're doing is the simplest form of regression possible. We're doing a least squares line fit to two-dimensional data. And basically in the top left-hand corner, well, all of these data sets are actually generating the same line fit, identical line fit, and the same residuals. So if you only looked at your error, you might think that you'd fitted the data equally well in each case. But you see, it's only the top left-hand corner where you can really say that that's true, where your assumption, in other words, that there's a linear relationship with noise, is true. In the top right-hand corner, you can see that there's, in fact, a nonlinear relationship, maybe a quadratic relationship, but where the nonlinearity is being interpreted as error residual. And on the bottom two diagrams, you can see you've got an outlier that is causing the fit to skew from the true distribution. So you'd ideally want something much more robust. So you can't treat it as a black box that you just look outside of and say, well, that's my fit and that's my error. It is always going to be a case of looking at the data. But we're in a position to essentially give a really definitive account of the relationship between regression and classification. So regression is building a general model of how a set of dependent variables change with respect to independent variables given a set of training data, or samples as they're more usually called in regression. Whereas classification is about building a general model of how a set of labels relate to a set of independent variables given a set of training data. So you can see essentially classification as being machine learning with a discrete output, and regression as being machine learning with a continuous output. But other than that, they're essentially the same thing. It is, of course, possible to have other forms of output. So maybe not just classes or continuous variables. Sometimes you might want to have an explicitly visualized relationship. This is some work of a student of mine looking at very high-dimensional data, diabetic data, and using a self-organizing map, so this tries to maintain locality, just to try and bring out visual relationships in the data. This isn't intrinsically meaningful from a classification point of view, or even from a mathematical point of view, but it is very good in terms of visualizing straight away whether you've got intrinsic patterns in the data. So that sort of thing is obviously relevant to visual analytics. You can also do completely unsupervised machine learning. That's where you learn classes from scratch. So you make no assumptions at all about what classes might exist in the data, you try and discover them. So this is obviously relevant to data mining. So you've got to come up with some systematic way of determining what the clusters in your data. Some algorithms like k-means require you to specify the number of clusters you're looking for, but there are others that will just find some sort of principled information theoretic way to determine what the intrinsic clustering of your data is. So I've used this, for instance, for showing that certain medical conditions that have been identified as a single syndrome are in fact multiple syndromes. If you can show that there's an intrinsic cluster and it's not just stochastic scatter. So the boundary between regression and classification is very blurred. And a simple illustration of that would be logistic regression. This is where you're fitting a sigmoid function to data that is either 0, 1 labeled or 1, -1 labeled. And basically, what this is essentially doing is deciding on a decision boundary. But it's giving you something like a likelihood in the sense that things closer to the decision boundary will have a more intermediate likelihood of being one thing or the other, but when you get further away from the decision boundary, you get a more definite allocation into one class or another. So this is very good for making discriminative classifiers pseudo-Bayesian. So it's used in a variety of different contexts like that. So it's often built on top of other classifiers. So there are essentially two different sorts of classifiers, generative and discriminative. Generative classifiers attempt to model the intrinsic variation in your data. So you build a model of each individual class, and then after that, you compute the best decision boundary. Discriminative classifiers, on the other hand, only attempt to model the decision boundary. They're not worried about how the actual distributions vary within themselves, the different class cluster distributions. So discriminative classifiers, and if there's one take-home message, it's basically use discriminative classifiers because they've got an intrinsically lower structural risk. Because they're not trying to capture superfluous variation in the cluster distribution, therefore they're less likely to overfit. So to give you an example, there's kind of a spectrum of classifiers that goes from nearest neighbour sport vector machines. So I'll talk about both of those. And every other sort of classifier that you've heard of, decision trees, Fisher and so on, will fall somewhere between the two. So to give you just an illustration of the working and the issues around the most generative classifier, the k-nearest neighbour classifier, was for many years a kind of workhorse classifier. It only works for very, very small feature sets, very low dimensional spaces. So typically n smaller than 8, which for a modern computer vision problem is absolutely nothing. I mean, you can have millions of dimensions. You typically also need a large number of training examples. But the idea is that basically you have a new feature vector, you have a new object come along, an unlabeled object. So this is always a goal in classification. You've got some unlabeled feature, and you're trying to attach a label to it. Is this person at risk of diabetes or not on the basis of your training data? So the simplest form of classifier is just to say, well, okay, I've got this vector. What's the nearest vector to it in my training data? I'll just give it the same label. That, as you might imagine, leads to an incredibly fragmented feature space. You can see by this Voronoi diagram. So here it's split up into the different class labels. And you can see this is a very, very long way from being a linear classifier. You've just got these little local regions around your training data. And as you can imagine, it tends to overclassify like fury. You can improve matters just a little by looking at more neighbours. So the next iteration will be a 3 nearest neighbor. So you ask, well, what are the 3 nearest vectors in my training data to, or exemplar vectors in my training set to this new vector I've got coming in, and you take a majority vote on the label. If it's a binary classification, that's always going to be resolved one way or another. You're going to get a definite classification. So you can use any odd numbers, 5 nearest neighbor, 7 nearest neighbor. You'd hope they'd get progressively better, and they generally do, but you're still not fundamentally solving the problems of nearest neighbor classifiers. And I've sort of glibly said, well, you talk about the nearest feature vector. Well, what does nearest mean? Your feature vector doesn't intrinsically define a metric, so you're free to choose pretty much any metric you want, and what works is going to be down to your problem. The simplest, obviously, is Euclidean metric, but there are plenty of others. Correlation distances, Mahalanobis distance, which takes into account the covariance of the class distributions, cosine looks at the angle between the feature vectors, and what works will be entirely data dependent. There's a no free lunch theorem here that says you can't simply say at the outset one classifier is going to be the be all and end all. It really is going to come down to your data. But that said, certain classifiers do have lower structural risk in most scenarios. So at the other end of the spectrum is the support vector machine, which is probably the workhorse of classification. And it's nice for all sorts of reasons. It's got low structural risk because it's a discriminative classifier. Mathematically, it's a nice convex Lagrange optimization problem. And it's very extensible through kernelization, which I'll get onto later. But basically, the simple idea is that you're trying to find the maximum margin hyperplane. Now, the margin is the distance between your class clusters measured orthogonally to your decision boundary. So trying to find the maximum margin actually defines a unique boundary, linear boundary in your decision space, characterized by just a few support vectors, and these drop out very nicely from the Lagrange optimization as the non-zero Lagrange multiples for those that work Lagrangian problems. So, but basically you'd see there's just a handful of points of vectors in your training set that are characterizing your manifold. And this is what gives it its very low structural risk. You're simply not, the rest of the training data has no impact at all on it. So, well, what if the problem isn't really separable? There are various things you can do. You can use soft margin, support vector machines, in which case you've got an extra configuration parameter to specify to cross-validation or something like that. But you can also kernelize and say, I'll come back to this, but you can project it in effect into spaces in which you can do things like guarantee linear separability. So I want to give an honourable mention to the perceptron, which is the first classifier. So this was actually derived from biological models of individual human neurons, human brain cells, modeling them very simply as a set of inputs into the cell, which are weighted, multiplied by a particular weight, summed, and then if this is greater than or less than some particular threshold, an output signal is sent. And it's actually a very simplified model of the human brain cell, but remarkably, it does actually act as a classifier in its own right. So you can see that if every single weight input to each, if you represent rather the input space as a feature space, then all of your weights are effectively components of that feature space that collectively give you a vector, a weight vector, which is this omega vector, that is defining a decision hyperplane. You've also got a bias offset in there. So basically, if you can train it, and you can train this very straightforwardly, and it's capable of learning. So that's a remarkable discovery that a single human brain cell, in and of itself, is capable of learning and acting as a classifier. And it can solve it can replicate some logic gates, Boolean AND problems, no problem at all. See, because if you represent it as an input space with your inputs on different axes, then the AND output is clearly linearly separable. So you can actually learn an AND gate using a single perceptron. You can't solve the exclusive OR problem, though, because when you represent it in a feature space, the exclusive OR gate, straight away you see that it's actually not linearly separable. So you couldn't solve it with any linear classifier, not a perceptron. So this was realized very early on. And the solution was to stack perceptrons and train them through backpropagating the error, the training error, down through the hierarchy. And you can use an output layer for classification, so it's very easy to get multi-class classification using output neurons. And you can see that it solves, because basically you've got different things happening at different levels, you can solve the exclusive OR problem. But backpropagation doesn't work for more than about 3 layers. It's got lots of problems with local minima that it can't get out of. So this basically means that neural networks go in and out of fashion in machine learning. They're suddenly back with a vengeance because there are now methods of deep learning for building multiple layer neural networks. And the secret is basically not to backpropagate, to basically forward encode progressively in stages and build up increasingly deep layers. And these seem to do other nice things like simulate very well how the human vision system works. And these, for certain kinds of problems, convolutional deep learners produce state-of-the-art performance, especially for image recognition. Classifiers you would often want to use as detectors. So this is where, I mean, say you might use this in a data mining context where you're trying to pull out certain patterns in your data. So in a computer vision problem, this might be, asking about pedestrians in footage, in vehicle footage for an autonomous vehicle, something like that. So here the binary classification is not, well, it is still between 2 classes, but essentially it's the presence or absence of that class that you're asking about. So now you're much more concerned with the behavior, the relationship between false positives and false negatives. So a false positive is when you've incorrectly said that something is there that actually isn't. You've hallucinated it. A false negative is when you said something is absent that actually was there and you've missed it. And the nice thing about classifiers is that it's fairly easy to turn those, to tune these to alter the ratio, the degree of concern you have between false positives and false negatives, which is something you typically want to do, especially in medical imaging scenarios. I mean, you think about the cancer detection I was talking about earlier. Clearly, the consequences of missing of a false negative is much more serious than the consequences of false positive. If you get a false positive, you can always ask a human to double check. So typically you want to tune the relationship between false positives and false negatives when you're using a classifier as a detector. And you can do that by permuting the classification boundary just by giving it a bias offset that essentially makes it either more specific or more sensitive. And you have what's called an RAC curve that looks at the ratio between false positives, false negatives, and allows you to tune where, in particular, you want your classifier to be depending on the scenario. In other words, how sensitive you are to false positives and false negatives. Another key issue in classification is the bias variance dilemma. It's also an issue for regression. This is basically the fact that as the model complexity increases, bias typically decreases. Bias is the systematic offset from, if you like, the true fit, or the optimal regression fit, or the optimal classification boundary, the Bayes boundary. So as the model complexity increases, typically your bias decreases. However, variance, that is to say, sensitivity with respect to different subsets or different permutations of the training data, will increase. In other words, you're starting to overfit. So pretty much always there's an optimal point somewhere between the two of those extremes where you've got just about the right number of parameters for the problem. So managing data complexity is very crucial in machine learning. Just to give you an idea, this is a typical sort of set of features for machine learning, for computer vision problem. You have about 128 million features per image until you start to quantize it. And that's just for a single image. You've got that potentially 30 frames a second. And if you're going through archive footage, like, say, all of the BBC's libraries, you can imagine how many dimensions we're talking about. And it's potentially enormous if you don't do something to manage your model complexity. So there are different strategies for that. Some models allow you to externally specify the number of free parameters, and you can use things like cross-validation or the Kayak information criterion to decide how to set a number of parameters. You can actually regularize your data beforehand, smooth it so that there are fewer issues with respect to the temptation of the classifier or regressor to overfit. You can do, as we've said, discriminative learning rather than generative learning. So if you're doing classification, you're not trying to characterize anything that's irrelevant to the classification problem. And the commonest standby, dimensionality reduction, stuff like PCA or kernel PCA, to reduce the size of the data. There are other possibilities, ensemble learning being one. This is where you split up the problem into different across different classifiers and combine their outputs. There may be natural reasons for doing that. You've got different modalities that have different classifiers within them. And then you combine their decisions together rather than combine the data together. So this is late fusion rather than early fusion. And sometimes, for various reasons, you want to do this deliberately as a way of managing the structural complexity of classifiers. One sort of approach is known as bagging, bootstrap aggregation. This is where you split your training set into different subsets, build classifiers, then combine the decisions, and that can reduce the variance of your classifier. So another approach, if you've got a very high bias classifier, is to look at boosting. So boosting is a meta-algorithm that basically takes an initial stab at classifying, at building a classifier, and essentially decides what is or is not well classified by that data, and re-weights those points so that you can then build another classifier that tries to characterize those awkward bits of data that you misclassified before, and then systematic ways for combining all of these together. You do this over multiple iterations, and you end up with a classifier with much lower bias. So you can use ensemble methods for managing both the bias and variance of classifiers. But finally, I'd just like to give an honourable mention to kernel methods. This, I think, is one of the most exciting areas because it's very paradigmatically different. So we've sort of assumed up to now that you've always got a feature space, that every particular object has a set of measurements associated with it. Not always the case. For instance, in genomics, how do you represent DNA strands as a set of feature measurements? Well, it can be done. You can look at various subsets, n-grams of different components, and create a set of histograms, which you then vectorize. So you can create features that capture some aspects of DNA strand, but not all of it necessarily. There are far more natural things to do. Like, for instance, it's much easier to compare two different DNA strands to say how different is this DNA strand from this other DNA strand. And that can be really useful because potentially DNA strands have different lengths, very, very different lengths. So a straightforward feature representation would potentially have different dimensionality, which would be a problem. But you can look at something like the mutation distance. You ask, what's the nearest common ancestor if you mutated at equal rates to create these two different strands of DNA. So you've got a similarity measure. And you could potentially do that for all objects in your training data set. You can make pairwise comparisons. So essentially what you end up with is a matrix of similarity functions. Now, there are certain classes of similarity functions called kernels that have very, very nice mathematical properties. In particular, if you have a kernel, broadly, with various conditions, most important of which is that the matrix you end up with is positive semi-definite, but providing this condition holds, and it does in that case of edit distance between genomics, then you can show that any given kernel is equivalent to an inner product in some space, in some Hilbert space. Now, you don't know what this Hilbert space is, and the beauty of kernel methods is you never actually have to compute it. If you've got any sort of regressor or classifier that is built around dot products, it is potentially kernelizable. And this means you can drop in, wherever you've got a gram matrix, which is a matrix of inner products, you can replace this with a kernel matrix. And this essentially extends the range of all of those algorithms. You can drop in whole different classes of kernels. Even if you have actually got a feature space, you can still use kernels and get this free injection into some new feature space, which may have properties that are more conducive to classification. So in the support vector machine case, you're effectively projecting, you apply your kernel, you project into some new embedding space, which may have properties like if you use a radial basis function kernel, you can guarantee linear separability. You actually generate an infinite dimensional Hilbert space if necessary to do that. And you carry out a support vector machine classification. You still got your support objects defining your decision boundary. But what you find is that if you had some original underlying feature space, an input space prior to kernelization, is that the decision boundary that is linear in your embedding space might well be deeply nonlinear in your original input space. So, you can get manifolds that look extraordinarily complex. But, normally that sort of complexity, if you try to emulate that with a polynomial, you would almost certainly be overfitting. But the beauty of kernel methods is that actually you're still only defining this complex manifold with just a very few support objects. So the structural risk is substantially minimized. So it's a very nice approach. So probably this and deep learners are the current state of the art. And depends, again, very much on the problem you're solving. Because this is the other take-home message, there is no free lunch. You've just got to see what works on your data. So just to summarize that, as we're probably getting close to lunch now, so machine learning is obviously starting to find its way into visual analytics. Lots of capacity to do all sorts of things. Pattern mining, trend discovery through unsupervised methods. Pattern recognition, where you want to classify discrete objects or detect particular types of patterns in data. And in prediction, where you're doing more regression type things, or another possibly is structured output learning, where classifiers can have more complex forms of output, like strings of labels, strings of class labels, rather than just single ones. And there is loads of existing methodology to draw on. I mean, I find, the methodology is piling up, just looking for data to apply itself to, and that's potentially a win-win situation in that, generally speaking, a new method is going to produce new things in an area like visual analytics, but equally visual analytics, I'm sure there are data sets that will present new kinds of problems that will develop machine learning theory and methodology. So I think it would be a very useful thing to look into further for those that I guess aren't using it already. So, thank you very much. Are there any questions?
Question.
So, I think one of the potential pitfalls of machine learning is not necessarily in the techniques, but in how they're being applied, which creates a lot of mistrust, I think, because it's very hard to understand these techniques. They've been treated as black box. So we may have something that's very accurate, but we actually can't explain it. So, do you have any thoughts on maybe the state of the art in that direction and playing with algorithms that are more explainable?
Yeah, I mean, this is always a danger. I mean, there's no substitute for really understanding what's going on inside the box. And if you just, I mean, you do see this everywhere in all fields. I'll chuck a support vector machine at it. And configuration parameters are set to defaults and so on. And, you'll get some result, which typically is better than what you were using before. But, there is no substitute for understanding the problem. But I think there are much more interpretative ways of using machine learning. For instance, in decision support platforms, you want a human to essentially do the labeling line. So you can imagine a human in the loop being presented with information. Potentially interesting things. If the machine learner is classifying, coming up with tentative classes rather than absolute classes, and presenting those through some sort of visual analytic interface to say, well, is this interesting? Then the user can essentially paint over those and say yes or no, that's not interesting. The classifier can go back and refine that. So, you can really do this in a very symbiotic way. And I think in visual analytics, I guess this is the way you'd be wanting to use it in practice. So you can do it in a much more online, human in the loop, rather than just tipping data into a support vector machine, which is, I guess, the least interesting way. And as you say, as I was illustrating with the cases of regression, you put in the wrong assumptions, you're going to get the wrong things out. You can't distinguish between error residuals and stuff that simply isn't accurately describing what the underlying trends of the data are.
Another question.
Out of the methodologies that you've shown, which one would you say is most suited for uncertain data? Data that have very high uncertainty associated with them.
Uncertainty in the sense of the stochastic
in terms of accuracy, and the sensor is not very precise.
Yeah.
So there can be errors in there, but you are not aware of.
So generally speaking, in a sort of standard pipeline, this is treated by dimensional management. So you embed everything you've got in some huge space, and then the first pass that most people would apply would be PCA. I mean, on the understanding that those axes of variance that have very low eigenvalues are probably not going to be useful for discriminative purposes, and are probably stochastic noise. So you have some sort of principal rejection, 2 sigma or 3 sigma rejection on eigenvalues. And that straight away, for most kinds of problems where data exists on quite a small manifold, you get orders of magnitude reduction of dimensionality. And that's a good first pass. There are more sophisticated things you can do. Kernel PCA, where you do it in a very non-linear fashion. After that, it's really about structural risk in the classifier and good features. So you can do it in much more classification sensitive ways. I mean, PCA doesn't take any particular view on the different class distributions. It's just treating the data en masse. And but it's a good set of assumptions for most purposes. In that the first pass will generally speaking, massively reduce the dimensionality of the problem. Get rid of instrumental noise.
Some other issue related to that. What if the sample of the population that you're treating is very small, so you don't have many data?
Yeah.
So you're basing your conclusion on huge data sets. What if your data is very small?
Well, this is a key issue. I certainly find this in healthcare. You have potentially very large feature spaces and very small patient cohorts. And the standard pipeline to say would be straight away to use PCA to reduce the dimensionality so that because straight away a lot of problems, a lot of classification. If you were trying to Gaussian fit your class distribution, if you've got fewer points than you have dimensionality, it's an ill-posed problem straight away. You can't even build a classifier. And if you added just enough points vectors to have the ability to do that, chances are you'd be producing extremely poor decision boundary that wouldn't generalize. So this is why I like kernel methods, because another issue is that particularly in areas like healthcare, where the dimensionality of the problem is much greater than the typical size of the patient cohort, the problem dimensionality is actually effectively the square of the number of participants, and it's not at all, because of the nature of kernel, it's not at all dictated by the dimensionality of your original feature space.
There's no risk that by using the kernel method you actually do the overfitting.
There is, it's not going to solve everything. There's still a risk, so you still want to get rid of extraneous dimensionality. I mean, there was a lot of excitement very long ago. Well, it'll never overfit. That's not quite true. You still want to do some sort of management. So first pass of PCA wouldn't hurt. But if you're using completely featureless kernels, then you just don't have a problem with dimensionality. You don't have a feature space. The kernel embedding will generate the dimensionality you need to solve the problem. And even when it does that, the structural risk is not great, because you just get a set of support objects in any case. So it doesn't mitigate all the problems, but it goes a very long way towards it.
Okay. Any other questions?
Worried about the fact that IBM could be building an enormous neural net that makes a lot of this irrelevant, because they're still used to it when there's technology which is totally outmatching my ability to analyze data better than something I could rent.
Well, yes and no. I mean, it's certainly a very big area of interest at the moment, deep learning, and certainly there are big corporations getting big hits because they can do massive amounts of training of these deep nets. That said, I mean, you can actually use off-the-shelf pre-trained deep nets. For instance, there are deep nets trained on image nets. So in terms of all the sort of hierarchies of image that there are. So, if you're going to solve a visual recognition problem, you can already use, to a certain extent, you can build your classifier on top of a pre-trained network. So you can treat that as an input and still do other stuff. I still think, there is no general solution. There never will be. Again, no free lunch. There is never going to be a completely general off-the-shelf solution. There's going to be no alternative to looking at your specific data and trying to build better features, better kernels to solve your particular problem. Because that then can be the input to a deep learner, or you can use that as a potentially a pre-trained deep learner as that IBM have produced or some such as an input potentially into your classification problem. So, it doesn't, I guess a few machine learners working in a few fields would be worried by this prospect, but I think in general, it's, there is never going to be a catch-all that will solve everything.
Okay. So let's, thank you, David. Thank you so much for that. That was very interesting. One of the tradition that we have at VASS is that each speaker receives a personally engraved whiskey tumbler.
Oh, lovely.
So here's yours. And
I shall christen it this evening.
please do. Yeah, thank you.